So if you're generating video today, you know the struggle, right? You want that stunning high-quality output from the huge, like, 13 billion parameter models, but they are just so slow.
They're incredibly slow.
Today, we're cracking open a source on a technique called FlowBlending. And the mission here is, well, to figure out how we can get that premium quality without paying that premium time cost.
And that's really the core problem. It's model capacity. The big models, LTX-Video and WAN 2.1, they give you perfect temporal coherence, great semantic details.
They're expensive.
Exactly. Computationally, they're a huge drain. Then you have the smaller, say, 2 billion parameter models. They're fast, but they often just fail. You get distorted objects, flickering.
Just not usable for high-end stuff.
Not at all. They just don't have the capacity where it counts.
Okay, so that's where this gets really interesting. This research found that you don't actually need that massive capacity, that supercomputer, running at full throttle the whole time.
Precisely. The key insight behind flow blending is what they call a stage-aware sampling strategy.
Sageware.
Yeah, think of it like a relay race, a 3-lap race, and you only deploy your fastest, strongest runner for the parts of the track that really demand it.
I love that analogy.
Yeah,
Okay,
right.
let's break that down. Stage one, the starting gun.
Yeah.
This has to be the large model. Why? What is it doing right at the start that only it can handle?
Well, this early stage is absolutely crucial. It's where the model sets the global structure and the course motion of the entire video.
Okay.
If you try to start small here, it's just a catastrophe. The schedules they tested that start small, which they call SLL, they often just completely ignore the text prompt.
So, like, you ask for a jellyfish in the ocean and you just get a blob.
A blurry, misaligned blob, yeah.
Yeah.
The large model is essential right there at the beginning to, set the alignment.
Got it. So the big gun sets the scene. But then, and this is the wild part, you switch to the smaller model. Isn't that like swapping out a race car for a scooter mid-lap?
It sounds like it, but that's the whole beauty of this intermediate stage. They found that once that main structure is locked in, this middle part of the process is capacity tolerant.
Meaning the small model can keep up.
It does more than keep up. The technical measure, the velocity divergence between the two models, is at its lowest point right here. In practice, that means the small, fast model is making updates that are virtually identical to the huge, slow one.
Wow. So it's just free efficiency.
Pure free efficiency. You're saving massive amounts of compute time.
Okay, so we save a ton in the middle, but then we have to bring the heavy hitter back for the final polish. Why does the small model fail right at the finish line?
Because the late stage becomes capacity sensitive again, but for a different reason?
Not for structure.
No, that's already locked in. This last stretch is all about refinement. It's about scrubbing out artifacts. If you end with the small model, the LSS schedule, you get these subtle but really annoying issues.
Like what?
Temporal flicker, some weird spatial distortions. So we bring the large model back, the LSL schedule, specifically to suppress those artifacts and refine all the high-frequency details. It's what gives the final video those, quote, more natural and realistic textures.
So it's basically a budgeting problem. You pay big upfront for structure, you save a ton in the middle when the work is easy, and then you pay big again for quality control at the end.
That's a great way to put it.
So what does this LSL flow blending strategy actually deliver? What are the hard numbers?
The results are pretty compelling. The quality, measured by things like FID and FED, is basically indistinguishable from running the large model the whole time. But the speed up, you're looking at up to 1.65x faster inference.
1.65. And even more importantly, that means it's using 57.35% fewer FLOPs. I mean, for you, the listener, that's huge. That could mean cutting your cloud computing bill almost in half for the same quality.
And that's the real aha moment here. The secret to faster, high-quality video isn't just a faster solver or a smaller model. It's about strategic resource allocation. It's knowing when to use the big, slow model versus the small, fast one.
What I find fascinating is how they figured out those boundaries. They used quantitative metrics, Dano similarity for the early stage to make sure the meaning was right, and FID to pinpoint where quality dropped off in the late stage. It really suggests that optimizing the compute schedule is becoming just as important as optimizing the model's architecture.
Absolutely.
But, this raises a final provocative thought for you to chew on. If these optimal boundaries were found empirically for these specific models, is there a truly universal, a model-agnostic way to identify these capacity-critical stages for any architecture? That's something for you to explore. Until next time.